Hello class, this is lecture 5E, Limestone and Liming. And in this video we're going to discuss or describe ways in which humans contribute to soil acidification, understand liming reactions used to raise soil pH, identify two measurements used to determine the need for liming, calculate a liming rate, describe the various liming materials based on their name and properties, list alternatives to liming and why they might be used, and describe methods to lower soil pH. So first, let's discuss fertilizers. So fertilizers can lead to soil acidification for a variety of reasons, but one is they generally are forms of weak to strong acids. Particularly this is the case for ammonium-based fertilizers. So let's look at ammonium sulfate, for example. So here we have ammonium and sulfate, and when that's combined with oxygen, we end up with HNO3, or 2 moles of that, which is nitric acid, H2SO4, so we have a mole of sulfuric acid, and water. So there, that's just one example of how we get both nitric and sulfuric acid being produced by adding ammonium sulfate. So that would be one way we can acidify soils. Also, organic additions, so adding, say, manure or compost, those can also cause acidification, and that can come from ammonium nitrogen oxidation, or the formation of organic and inorganic acids during the decomposition process. So those are ways we can acidify soil through fertilizer amendments. Soils can also be acidified through acid rain. So acid rain is caused by industrial gases that contain nitrogen and sulfur that, when they're released to the atmosphere, eventually turn into nitric acid and sulfuric acid. So the reactions that cause that are shown in this figure on the right. So here we have sulfur eventually producing, or in combination with sunlight, eventually producing sulfuric acid, and N2O emissions going through these chemical reactions in the presence of sunlight, eventually creating nitric acid. So when we have sulfur and nitrogen emissions coming from typically the burning of fossil fuels, whether that be gasoline or diesel or coal, all those emissions, if they're containing nitrogen or sulfur, can produce acid, which then gets dissolved in rainwater as it falls down to the earth. And as those acids acidify the soil, it's producing hydrogen, and those hydrogens are cations that are exchanging with the base cations. And as we acidify the soil, those base cations are able to be leached out. And so over time, we get more and more leaching and more acidification of the soil. And when we have this nitric acid and sulfuric acid, it can lower the pH of the rain down to a pH of 2 to 4, as opposed to normally about 6 to 7 for a pH for rain. So it can lower the pH significantly. So again, acid cations displace calcium on the CEC, and this is particularly problemsome for areas that are forested, because trees actually need a lot of calcium, and so it can leach the calcium out of the trees and actually make calcium one of the more limiting nutrients in forest environments. But also the calcium is one of the base cations, and as we lose that, our soil just becomes more and more acidic. And also, in the absence of calcium, aluminum toxicity becomes more and more of a problem. So calcium helps to offset some of the issues that used to be a problem for trees. Another way we can acidify soils is through acid sulfate materials. So acid sulfate materials come from, they are pyrite-containing materials. So pyrite is iron sulfide. So here we have FeS2. And so if we have iron sulfides that are in some sort of, say, mine tailings, or another common location for this is in material along the coast where there's lots of sulfur present from the seawater, and if there's lots of iron present, if it's in a reduced form, it creates this iron sulfide. And as that material is, say, dredged to make a canal or to make a deeper harbor or to build up areas to build houses on so they're not sitting in the seawater, all those activities are stirring up materials that contain this iron sulfide. So it could be activities like along the ocean, or activities such as mining that brings these pyrite-containing materials to the surface. And in all these cases, we have this iron sulfide that would normally be in a reducing environment, but when it gets exposed to oxygen, it reacts with the oxygen and water, and just 2 moles of iron sulfite create 8 moles of hydrogen and 4 moles of SO4 2 minus, and then 2 moles of FeOH3. So basically we're creating more or less 4 moles of sulfuric acid, which is a strong acid, all from 2 moles of iron sulfide. So we can create some very acidic materials really quickly. So again, it's commonly occurs in coastal areas, and also can occur from dredging, excavation, dewatering, housing and marina developments, and mining areas with pyrite materials. All right, so I have a review question for you. So this was covered in our previous lecture, but I just want to get you kind of back in this mindset of how lime works. So what gas is emitted during the liming process, which causes the equilibrium equation, or equations, I should say, to be driven to the product side, i.e. forces a rise in pH. Oxygen, nitrogen, carbon dioxide, hydrogen sulfide. So I'll give you a second here. If you need to, feel free to pause the video and look back through your notes before I show you the answer. All right, the answer is carbon dioxide. And the slide that we discussed this in the last lecture is shown here. So if we add ag lime, or just limestone, calcium carbonate, we produce carbonate, bicarbonate, H2CO3, and eventually water. And in the process, from 1 mole of lime, we're producing 2 moles of hydroxide, which can then neutralize 2 moles of acidity, 2 moles of H+. But the end product is carbon dioxide. And all these are equilibrium equations with the arrows going both directions. So it can go either direction depending on the conditions. But if we remove a product, in this case carbon dioxide, by allowing that CO2 to off-gas to the atmosphere, this whole reaction sequence moves towards the end products, water and CO2. So this is why when we add limestone or lime to the soil, it does in fact raise pH and doesn't just stay as calcium carbonate typically. Okay, so let's discuss liming. So liming is where we're taking the soil pH and we're trying to raise it by amending the soil with alkaline materials. And these materials generally are what we call conjugate bases of weak acids. So carbonates, hydroxides, or silicon oxides. Most commonly, it's carbonates or hydroxides. And when these react with the soil and the soil solution, it's going to consume hydrogen, and it'll form weak acids like water. So it's going to consume the H+. So most reactions initially react with CO2 and water to form bicarbonate. And an example would be dolomitic limestone. And so here we have dolomitic limestone where there's both calcium and magnesium attached to a carbonate. And that reacts with water and CO2. And we eventually get that associated calcium, that associated magnesium, and then we have bicarbonate that forms as well. And that bicarbonate is what goes on to neutralize that acidity, like I shown you in the previous slide. So the calcium and magnesium are important here because they displace the acid cations in the CEC. So we're adding cations. Those cations have to be in equilibrium with what's actually absorbed onto the CEC. And so as they reach the equilibrium and release hydrogen, the hydrogen goes into solution and it's available to be neutralized by the carbonate. And then the end product is CO2, which gets emitted as a gas, allowing this reversible reaction to proceed forward. So to kind of illustrate this further, so initially we have a colloid, so we have some stack of clays, and on the exchange sites we have, in this case, hydrogen and aluminum. If we're adding calcium, so 2 moles of calcium and some bicarbonate, then those calciums are going to exchange with the hydrogen and aluminum. So we get calcium that's absorbed onto the colloid, and the aluminum and hydrogen have been kicked off into solution, and we neutralize the acids, and they form aluminum hydroxide and water. So those aluminums and hydrogens are still present, but they are in a form that is no longer causing acidity. And then we end up with CO2 as a gas that gets emitted. So this whole reversible reaction goes to the right. So there are 2 liming questions that we need to do, or we need to ask ourselves when we're trying to manage soils. So one is, what is my soil pH? And to do this, we have a couple different tests. We talked about those briefly in our last lecture. Generally what we do is do a pH electrode measurement on a soil slurry, where it's a 1-to-1 ratio of soil solids and soil liquids. So say 10 grams of solid to 10 grams of liquid, something like that. And so we make this slurry, we stick in a pH electrode which measures the active acidity. And generally, if the pH is less than 6.5, then we know that we need to do some lime. If it's more than 6.5, then generally we don't need to do lime. That does depend on what crop we're trying to grow, and also it depends sort of on what part of the state we're in. So in Kansas, we actually have different cutoff values. In some parts, it might be 6 is the cutoff. In other parts, it might be 6.8 or 6.5. So in most states, it's usually around 6.5 is kind of the cutoff. All right, now how much lime do I need is the second question. So if it is in fact acidic, and we have a pH that's lower than 6.5, so slightly acidic is okay. If it gets too acidic is when we get a problem. So if it's too acidic, then we need to add lime. And then the next test is what we call a buffer pH test. And this essentially assesses the amount of hydrogen that is on exchange sites, or the exchangeable hydrogen. And how it works is we add a salt solution, this pH buffer, and this pH buffer contains cations. Those cations exchange with the hydrogen, kicking them off in a solution, and that is going to lower the pH. And the degree to which the pH changes in this buffer solution tells us how much exchangeable hydrogen is on the soil. And we could use that with some equations to figure out exactly how many, say, moles of lime are lime, and coarser textures need less lime. So looking at this figure on the right, if we have a clay loam, the soil has a CEC of 25, and at a CEC of 25, it's going to take a lot more lime to neutralize that soil. So say if we start off at a pH of 4.5, so on the y-axis here we have pHs of 4.5 to 7. The solid dark line is the clay loam. And if we're starting off at 4.5, we would need to apply 20 megagrams of lime per hectare to raise the soil back up to a pH of around 6.5. But looking at a sand, or even a sandy loam, we have CECs of 5 to 10, and so we would need about 4.5 to 7 megagrams per hectare of lime to raise that soil to a pH 6.5. So basically, 4 times as much lime to neutralize the clay loam as we would have for the sand or a sandy loam. So the more CEC we have, the more buffering capacity the soil has, which means it resists resists change to pH more, which as a result requires more lime to neutralize it. Oops, sorry. So ECC, effective calcium carbonate, CCE, calcium carbonate equivalent, and FF, fineness factor. So ECC is what we're trying to get to, but we have to factor in the CCE and FF. So let's talk about CCE next. So calcium carbonate equivalent. So this is basically the test that we do, or the value that we use to compare the purity of different liming agents. And calcitic limestone, calcium carbonate, is the most common lime used. And because of that, we sort of use it as the gold standard. And so all other lime agents are compared to calcium carbonate in terms of their effectiveness. So if they have a CCE that's higher than 100, that means that they're more effective at neutralizing acidity. If they have a CCE that's less than 100, then they're less effective. And so calcitic limestone is, relative to itself, is 100% effectiveness, 100% effective. Dolomitic limestone, it's very similar to calcitic limestone. The one difference is that it has magnesium present instead of only calcium. And so basically within a small kind of standard error, it's pretty much the same effectiveness as calcitic limestone. So 95 to 108 CCE. The advantage of dolomitic limestone is if you have plants that you're growing that have a magnesium deficiency, you can both neutralize the acidity and fertilize with magnesium all in one shot. So that's the big advantage with dolomitic limestone. Burned lime is created by taking calcitic limestone and burning it. And the end result is the carbon that was in that carbonate, the carbon is actually burnt off as CO2, and we end up with calcium oxide. This is sometimes called quicklime because it's a lot more reactive and it works a lot faster. So it's more expensive because there's energy costs that go into burning that limestone. But if you want the pH changed immediately, burn lime or quicklime is the way to go. Now, 1 mole of calcium oxide will neutralize 2 moles of acidity. Same as calcium carbonate, 1 mole of calcium carbonate will neutralize 2 moles of acidity. But because calcium oxide has a lower molecular weight, that means that for, say, if we have 1 gram of calcium oxide versus 1 gram of carbonate, we're going to have more moles of calcium oxide. So on a per mass basis, calcium oxide is more effective than calcitic limestone. And as a result, we get a higher CCE. So on a per weight basis, it is more effective and we get a CCE that's higher than 100. And it all comes down to that molecular weight of calcitic limestone. All right, the next type is hydrated lime. And this is also fast acting, and it's made basically by taking calcium oxide and processing it further. And they take calcium oxide and they slake it with hot water. And again, it costs more. It's not quite as effective as burned lime in terms of CCE. So, but in some cases that might be the only source. And some of these are just waste products from other industrial processes that you can buy and use, or be given from a company that's trying to get rid of it, and you can use it as a liming source. So that's why you might do something like hydrated lime. Down at the bottom, we have 2 more sources. One is more common if you were in an area that is close to the ocean, or in some time of the geologic history was close to the ocean, where there is lots of marl present. And marl is seashells that have concreted together. So you can actually recognize individual shells, and then those shells are bound together with other calcium that's precipitated that has cemented together all the shells together. So you have this big chunk of seashells. And those can be ground up and applied to the field just like lime. But there are impurities to it where not all of it is actual calcium carbonate, even though seashells are made out of calcium carbonate. And so the CECE is less effective than calcitic limestone. And then at the bottom, we have wood ashes. So these are generally things that have been burned, and those burned products can be applied to a field. So they range in CCE, but usually they're around 40, and they are water soluble, and they contain. There's lots of different types, so it just kind of depends on what exactly is being burned. All right, now, so we have all those different CCEs that are all a measure of purity or effectiveness of different liming agents. Now that we have the CCE, we can determine a liming rate. So let's say that a soil test recommends 4 tons per acre, and that is referencing 100% effective calcium carbonate. And we have a limestone that's available from our local distributor, and the distributor tells us that it has a CCE that's 90%, meaning that it's 90% pure, or 90% effective relative to pure calcium carbonate. And the sieve test shows that if we have a sample that was originally 100 grams, the amount that was retained by an 8-mesh sieve, the coarsest sieve, was 5 grams. The 8 to 60 was 30 grams, and the stuff that was finer than a 60-mesh sieve was 65 grams. So let's calculate the fineness factor. So fineness factor, we have 5 grams times 0% effectiveness for coarse materials, plus 30 grams times 0.5 for 50% effectiveness, and then 65 grams times 100% effectiveness. And the sum of those, sum of all that is 80. So that means that just based on particle size, our sample or our limestone would be 80% effective compared to material that might be ground more finely. So 80% effectiveness just due to particle size. And then the next thing we need to do is calculate our effective calcium carbonate for this particular source. So to determine that, we multiply our calcium carbonate equivalent, which was 90%, and our fineness factor, which was 80%. So 0.9 times 0.8, we get 0.72. And that means that our lime is 72% effective relative to pure calcitic limestone that was ground fine. So we have a 72% effective lime source. The last step is to adjust our liming recommendation. And so to do that, we set up an algebra problem. So we have our 72% effective lime times some unknown mass of lime, application rate, equals 4 tons per acre. And so if you think about this, if we have a lime that's only 72% effective, we're going to have to apply it at a rate that's higher than 4 tons to get that same 4 tons of ECC that was recommended based on the soil test. And so we put 0.72 times x equals 4. We solve for x, so take 4 divided by 0.72, and we get 5.6 tons per acre. So this would be our new application rate based on 90% effective CCE, 80% effective fineness factor, giving us an ECC of 0.72. We plug that into our algebra problem, and we get 5.6 tons per acre. All right, now I want you to go ahead and try your hand at this. I set it up for you. So we have a new sample 85% effective. We have mesh sizes where coarse material was 10 grams, medium was 20, fine was 70. So go ahead and calculate your fineness factor, calculate your ECC, and then and our soil test recommendation was 6 tons per acre. So you plug in 6 tons per acre here, and your ECC here, solve for X, and that'll be your new application rate. So go ahead and pause the video here and calculate that on your own and see if you get what I calculate on the next slide. All right, so plugging in our values, 10 grams times 0% effectiveness, plus 20 grams times 50% effectiveness, plus 70 grams times 100% effectiveness, we get an 80% fineness factor. So we had different values in the last one, but we still get 8%. And then our ECC, we took 85% from our CCE times 0.8, or 80% from our fineness factor, and we get 0.68. 0.68 times X equals our recommended rate, 6 tons per acre. Solving for X, we get 8.8 tons per acre is what would be required given our soil test recommendation and the values for our lime from our supply. Okay, so now you know how to calculate a liming rate. The next thing I want to cover is some other liming considerations. So one is we don't want to add too much lime at once. So generally it's recommended that we don't add more than 4 tons per acre a year. And in both the two examples I showed you prior to this slide, both of those were over 4 tons per acre. And so in that case, what we would do is we would apply at 3 to 4 tons per acre on 2 to 3 year intervals, and we would just keep on liming regularly until we've neutralized the soil. So we don't want to apply too much at one time, otherwise it'll not dissolve fast enough and not react fast enough to get the full effect from the lime. So we don't want to apply more than 4 tons per acre per year. And one thing to consider too is if we use tillage, then we're basically liming the top 6 inches because we're kind of mixing the top 6 inches of the soil. But if we have no-till, then no-till doesn't actually allow the lime to be fully incorporated into the soil. However, there's one caveat. So in no-till operations, we generally have higher worm populations, and the worms will come up to the surface, they'll take a bite of crop residue, and that crop residue, if it has lime on that residue, the worm is going to pull that residue down below and incorporate it for us, or the worm's going to consume that lime and then bring it down below as a worm casting. So worms are our friends in terms of incorporating lime for no-till operations. Also, this takes a while for lime to react. We want to allow at least 6 months for lime to react to get the full effect on the soil pH, if not a whole year ahead of time. So we don't want to apply lime like we do for, say, nitrogen fertilizer, where it's right around the time that the crop's planted. Instead, we want to apply it 6 to 12 months in advance so that it has time for that lime to actually react and neutralize the pH. There are also alternatives to fixing lime or fixing acidity problems with soils. Most acidity occurs near the surface where liming reagents can be mixed, but we can also have issues in some parts of the country with soil acidity problems that are deeper. And so that can cause some issues, and it's more difficult to get lime that deep in the profile to neutralize that acidity. So one product that's used for that is gypsum. So calcium in the form of gypsum is a lot more soluble than calcium in the form of calcitic limestone. So gypsum is CaSO4, and gypsum is more soluble. So the calcium from gypsum is more soluble, that allows it to be leached down into the lower parts of the profile to depths that we would not be able to to incorporate lime through tillage or other operations. Now, gypsum is not considered a liming agent because it does not change the soil pH. Gypsum does, however, help alleviate some of the symptoms of acidity. So again, gypsum, actually I have a typo here. It's not CaCO4, that's acidic limestone. It should be CaSO4. So gypsum is CaSO4, and it is a neutral salt, meaning that it does not change the pH of the soil. But it's more soluble, so it can actually move that calcium down into the subsoil. And one of the biggest issues we have with soil acidity is aluminum toxicity. And calcium offsets the issues that we have with root stunting and cell division at the root tips that's caused by aluminum toxicity. And so it does not raise the pH, and so it is not a lime agent, but it does alleviate the symptoms of lime. Or just, excuse me, it does alleviate the symptoms of soil acidity. And this is very common in regions that have a lot of ultrasols and oxasols, because in those regions, the soil pH generally will decrease as you go lower and lower in the profile. And so we do get soil acidity issues at depths that we cannot manage through incorporating limestone. And so gypsum is commonly used in those parts of the world. Organic matter, we discussed it previously as being a source of acidity. It can also be used as an alternative liming agent. So this is used a lot more when we have like resource poor farmers that can't afford to buy lime or calcium or gypsum even. But if they can have a way to create compost or to add organic matter from other sources, that can help alleviate some of the issues. So organic matter will bind tightly with aluminum, which as a result limits the toxicity of aluminum. And also the lower molecular weight organic acids that come from decomposing organic matter will form these soluble complexes with aluminum. So it complexes the aluminum, making it less available. And also organic amendments can contain calcium, and that calcium, because it's usually complex, will actually make it more soluble to be transferred down to lower horizons, which also helps to alleviate some of the issues with aluminum. And again, this can be a good option for resource poor farmers. So if you're working in, even in Kansas, where in some areas it's hard to actually get limestone, but also around the world, if you're in an area where it's logistically impossible to truck tons and tons and tons of limestone to neutralize the field, if you have the ability to add organic matter, then this is a good way to alleviate those acidity problems. It doesn't fix the acidity problem. It helps with the symptoms of acidity, namely aluminum toxicity. Another strategy is to select adapted plants. So you can change what plants are growing on a landscape to plants that are more tolerant of acid conditions. So this is another strategy. So just changing what's grown, and also people can breed or genetically modify plants to tolerate more acidity and more aluminum toxicity. So this is becoming increasingly important in tropical environments where liming is just economically impractical. Another consideration with liming is that we have to reapply. So in most settings, we're applying fertilizer to the soil, and the fertilizer is going to continue to acidify the soil over time. And we have to manage the pH by regularly applying lime. And so if our goal is or if our optimum pH is say 6.8, then our liming and soil pH would look something like this. So we add limestone at year 0. Our soil would go from acidic pH up to say 7.5. And then we add more fertilizer each season. The soil gets more and more acidic, There's more base cations being leached out from rainfall, and eventually we get down to our trigger point where we're below, say, 6.5 or 6.0, and we apply limestone again, and this is year 4. And so we apply more lime. It takes about a year for that to be 100% used up, and our soil pH goes back up. And so the goal is to have our soil pH basically go around our target pH. So it goes up and down, but in most years it's relatively close to our optimum pH. So we have to relime to manage these soil pHs. All right, now one final topic related to soil liming and limestone is lowering soil pH. So in some situations we actually want to acidify the soil, and this could be in arid areas. Soil alkalinity can be a problem, particularly if we have sodic soils. And some crops actually prefer acidic conditions, or some crops and some plants, ornamental plants. So examples are rhododendrons or azaleas. We can change the color of the flowers depending on the soil pH for those. And also blueberries. If you want to grow blueberries in Kansas, blueberries are adapted to a really low pH, so a pH of less than 5. And the best way to do that is either grow blueberries in a container with sphagnum moss that has a very low pH, or to grow them in the ground, but only after you acidify the soil. And we can do this by adding acidic organic materials. So this could be pine straw or acidic peat moss or pine sawdust. But we can also add minerals to the soil, like aluminum sulfate, commonly called alum, or ferrous sulfate, FeSO4. And excuse me, my mic just turned off on its own. So yeah, my microphone just turned off. So sorry if there's a cut off there in the audio. So we can add inorganic chemicals like aluminum sulfate, alum, or ferrous sulfate, FeSO4. And these, when they're added to the soil, they'll oxidize and will create acidity, and that will lower the pH. So we get hydrolysis. So an example would be if we wanted to add elemental sulfur, which is another inorganic chemical, then elemental sulfur, when exposed to oxygen, will create sulfuric acid, and that will lower the soil pH. So alum, ferrous sulfate, and elemental sulfur, those are all things that we can apply to the soil to lower the soil pH. If, say, you wanted to grow blueberries in a Kansas soil that formed from limestone. So it is possible, but usually not at a large scale, because these materials do cost a lot, but it is possible. All right, I have a review question and then a discussion question. So, review question: aluminum toxicity is a problem with low soil pH. What does aluminum do to a plant? So your options are limits the ability to produce chlorophyll, binds and precipitates nitrate, making it less available to plants, stops cell growth at the root tips, or makes iron less available to plants. So the correct answer is aluminum stops cell growth at the root tips, and as a result stunts the root systems of our plants. All right, now the graded discussion from this lecture, I want you to explain why gypsum, calcium sulfate, is not a liming agent, but is used as a liming alternative. So why is it not a liming agent, but is used as a liming alternative? So explain that in the graded discussion on Canvas, and that will conclude this lecture.